While solving the ordinary differential equation as well as partial differential equations, we very frequently come to this tri-diagonal systems of equation, which means that only the diagonal of the coefficient matrix and the left and right side of the diagonal terms will be populated. Rest of the elements in that coefficient matrix will be zeros. So we have all zeros here, all zeros here. To solve such system of equation, we usually use a technique that we call Thomas algorithm. And Thomas algorithm is designed based on Gaussian elimination. We can say it's a simplified version of Gaussian elimination, which was originally proposed by Lewin-Thomas, and in his name we call this Thomas algorithm. The idea here is that we go with forward elimination and back substitution as we did in Gaussian elimination. We start with the goal of making this A's to be zeros. So I use B1 as a pivot element, I make A2 0. Then in next step I use B2, which is now modified as a pivot element, and I make A3 to be 0, so on and so forth. So all the A's will be 0. When all the A's are 0, we can see in the last equation we have all zeros. In the coefficient matrix we only have this diagonal term Bn. Of course Bn will be modified by then. All the B's will be modified in this forward elimination through this Bi minus Ci minus 1 multiplied by R. What is this R? We will talk about it quickly. And because of this forward elimination, D's on the right hand side will also change. In the same way, Di minus 1 multiplied by R. And once we make all these A to be zeros, from the last equation we have only Bn, which is now modified. Then we have Dn on the right hand side, which is also modified. But I can calculate Xn from this Dn by Bn. Then I come to the previous equation and I calculate Xn minus 1. Xn is now known. And then I can go to n minus 2, etc., etc. So I can carry out a back substitution just as we did in Gaussian elimination. So Thomas algorithm, as we'll see quickly, that this is a simplified version of Gaussian elimination. Let us see how to do it. Okay, first of all, even before we do anything, we have to store this matrix in a computer. To store this matrix, we should not store all these zeros. They will only take space that are unnecessary. And that is exactly why we don't want to make these zeros to be non-zeros anytime during our calculation. So these zeros will always remain zeros. And what we do is that this coefficient matrix A, it can have at max 3n non-zero terms. So we can have 3 one-dimensional arrays to store this coefficient matrix. So as we have discussed in our previous lecture, that if this is an n cross n matrix, we have n square elements here, but only 3n elements could be non-zero. So we'll have 3 one-dimensional arrays. Each array will have a dimension of n. Now our goal is to make these A's to be zeros, and that is the step what we call is forward elimination. So how can I do so? So for instance, I take this equation 2, which means row 2 in our coefficient matrix. Now I multiply this equation 1 into A2 by B1, and then I take that out from equations 2. So my new equation 2 equals old equation 2 minus equation 1 multiplied by A2 by B1. If I do so, then in new equation 2 my A2 will be 0. And I don't write that explicitly. I'll simply not use A2 anymore because A2 is 0. B2 is changing. B2 will be the old B2. This is my new B2. It would be old B2 multiplied by this C1 just above B2. There is C1. So multiplied by C1 into this A2 by B1. C2, of course, there will be no change in C2, and D2 will change. D2 will be old D2 minus D1 multiplied by the same term A2 by B1. So now I have a new equation 2 which will replace the old equation 2. After we replace it, I can see that here I have 0. My B2 and C2 and D2, all of them have changed. C2 remains same, so there is actually no change in C2. C2 remains same, but B2 and D2, they have changed. A2 becomes, of course, 0. We can carry out the same thing for equation 3. At this point, I'll use this B2 as my pivot. So I have this new equation 3 will be old equation 3 minus equation 2 multiplied by A3 by B2. With this A3 by B2 multiplication, my new A3 will be 0. B3 new will be old B3 minus C2 is just above B3. So C2 into A3 by B2. C3 will remain same. D3 will change. This would be old D3 minus D2 multiplied by A3 by B2. So now we are ready to generalize. So we don't do anything in the first equation or in the first row of the matrix. I start from I equals 2. First row I give this as I equals 1. Second one is I equals 2. I go from I equals 2 to n, and I define this R as AI BI minus 1. Just like here you can see this is A2 by B1. Here it is A3 by B2. So for the row I or equation I, my multiplication factor is AI divided by BI minus 1. Then my new BI will be BI, old BI minus CI minus 1 multiplied by R. So we can check it here. B2 equals B2 minus C1 multiplied by A2 by B1. So in case of B2, here it is C1. In case of B3, here it is C2. So in case of BI, here it is CI minus 1 multiplied by this multiplication factor R here. Similarly, DI is DI minus DI minus 1. You can once again check here. D3 is D3 minus D2. So DI is DI minus DI minus 1 multiplied by the same multiplication factor R. We are not going to write anything for A and C because we know that C remains same and A equals 0. We are not going to use A, but we are not going to spend futile calculation by calculating A. We know that A will be 0. Okay, so now that we have the forward elimination complete, once we run this through, what will have, all the A's will be gone here. So we have lots of zeros, and in the last equation you can see that only the diagonal element will survive, that is the Bn will survive. This Bn is of course not the old Bn, this is a new Bn. After the forward elimination, this Bn has changed with this Bi minus Ci minus 1 multiplied by R. With this calculation, the Bn has changed now. Also the Dn has changed. So this B, C, D are of course different. C's are not different. C remains just the same. So C is same, but D and B have changed. Okay. We can see that the last equation we have no problem. We can now solve this last equation and find xn as dn by bn. Okay then. So what we are going to do for x n minus 1. We can come to this equation n minus 1 here. Here this equation actually represents b n minus 1 x n minus 1 plus c n minus 1 x n equals d n minus 1. So now that x n is calculated from equation n already, I can use this equation n minus 1 to calculate x n minus 1. So x n minus 1 will be d n minus 1 minus of c n minus 1 x n divided by b n minus 1. Similarly, for n minus 2, I can have x n minus 2 d n minus 2 minus c n minus 2 x n minus 1, which I have calculated before from here, divided by b n minus 2. So now we can generalize. First I have to get xn as dn by bn, and then I go from n minus 1, n minus 2 all the way up to 1. So this is our back substitution, and my xi is di minus ci xi plus 1 by bi. So we can check it out here, xn minus 1 dn minus 1, so xi di, then dn minus 1 minus cn minus 1 xn, so xi di ci and xi plus 1 divided by bn minus 1, so bi. So bi of course cannot be 0 at any point. The algorithm will fail in that case, and in fact in that case we are not going to have solution. You use Thomas algorithm or something else, you are not going to have solution. Okay, so now that we understand how this algorithm works, you can try a small exercise by writing a pseudocode for Thomas algorithm, which will be also part of your next homework, and then you write a computer program to solve a system of linear equation using Thomas algorithm. And finally you validate your program, which means that you write a program to solve a system for which you know the results, and then check it out that if the known results are being generated by the program. So that's all for this lecture. Thank you, and I'll see you in next class.